Hello, everyone. I think we are live now. Welcome to the Energy Distribution and Infrastructure session as part of this ETP annual conference. My name is Panagiotis Papadopoulos, or Panos for short. I'm a senior lecturer at the University of Strathclyde, and I will be chairing this session where we have various interesting talks from speakers from University of Glasgow, Glasgow Caledonian University, University of Edinburgh, and University of Strathclyde. We have 2, 3, 4, 5, 6 speakers today with us. Each one of them will have about 15 minutes, including questions. So 10 plus 5 is going to be the standard format that we're going to be following to present their work. And then after the 10 minutes presentation, they will have another 5 minutes to basically get any questions. I think you will have the option to speak up if you want to, unmute yourselves and pose any question that you would like to the speakers. If you find it easier or you're more comfortable, you can always use the discussion forum function where you can type a question, and following the presentation, I will try to coordinate, so pass on the question to the speaker and then coordinate the answers. I think this is about it in terms of managing the session. So I probably shouldn't be wasting any more of the session time. So I will open up the stage to the first speaker, who is Khalif Ali, if I'm pronouncing this correctly. Khalif is from the University of Glasgow, and he's going to present his work about high precision fault localization. So I don't know if we have Khalif on the stage yet. Right, there he is.
Hi there, good afternoon. My name is Khalif, and today I'll be presenting my project titled High Precision Fault Localization in Underground Power Cables Based on Wireless Power Transfer Technology. My presentation will cover the following headings, starting from introduction all the way down to remaining work. So, starting from introduction. Faults in underground power cables bring a plethora of socio-economical problems, starting from loss in supply to hazards of electroshock. Hazards of electroshock vary from minor shocks to injuries to death or even explosions if faults cause arcing near leaking gas pipes, as you see in the video below. Loss of supply is made of two main segments: customer interruptions, CIs, and customer minutes lost, CMLs. As we can see from the trends provided by Scottish Power Energy Networks, the actuals seem to be reducing. However, the marginal differences between the actuals and the targets set by Ofgem also seem to be narrowing, and there also seem to be some spikes in turbulent years. Nonetheless, distribution and network operators such as Scottish Power Energy Networks, etc., have to pay fines and penalty fees to Regulation Authority Ofgem for loss of supply. And in 2018-19, this was £22.8 million for Scottish Power Energy Networks. So, finding faults quickly and accurately are essential to ensure safety to the public, to secure supply to the customers, and to reduce expensive penalty fees. The aims and objectives of this project are to mitigate the problems of the present fault-finding methods. We propose a new technique, which is non-destructive, robust, and offers high precision in fault localization. We propose a mobile wireless power transfer device, which is capable of inducing power into the faulted cable, and by integrating power monitoring system, by an integrated power monitoring system, a scanning process can take place to find the fault. So I'll now discuss a little bit about the industrial fault-finding techniques already presently existing. So the fault-finding process is based on two main processes. One is pre-location, which is to obtain a fault location estimation, and the second is to actually pinpoint onto the actual fault point. State-of-the-art pre-location uses TDR and thumping. The limitation of TDR is that it can be inaccurate, and it can also be difficult to interpret. Limitations of thumping is that it can be destructive to the cable and may initiate dormant faults, and it can also be detrimental to the residential loads as well. The state-of-the-art pinpointing uses thumping as well, and this faces the same limitations. The only alternative to this is the sniffer method, which is primarily used for low voltage distribution network because thumping is dangerous to domestic appliances. The sniffer method finds the fault by analyzing the gas that is given off at the fault point. However, the limitations of the sniffer is that the gas can escape from the ground, and sometimes the gas can get trapped in conduited cables, which are in ducts. The last resort is the cut and test method, which is exactly as it sounds. It's highly destructive to the cable, can cause excess escalations, traffic disruptions, delays of finding the fault of over a day, and excess costs of nearly £1,000. So the proposed solution. We propose a device which is able to induce current into the faulted cable by means of electromagnetic induction. And if you consider that the cable consists of 3 different sections, one section for each side of the fault and the faulted section itself, the induced current can be monitored at any cable end and by the device itself. And as the device moves from one section to the other section, there'll be a change of current profile, which is monitored from the device or the cable, and hence the change in current will indicate the position of the fault. I will elaborate this further with a fault scenario. This is a short circuit fault scenario, and as we see in the diagram, the cable conductor is being monitored, although the device can also be monitored as well. And the current induced into the cable, the current induced into the cable can be monitored, and the value can be taken as a reference current. When the device moves to the top of the fault, the current value in the cable may peak up to double the reference current. And then when the device moves to the right-hand side of the fault or the other side of the fault, the current value would decrease from the peak, yet be different to the reference current. Similar to open circuit fault scenario, case studies provided by Scottish Power have proven that when an open circuit fault occurs, one section of the cable or one side of the fault is likely, not always, but likely to become short-circuited, and whereas the other side will be open-circuited. And sometimes both of them can be short-circuited. It depends on the fault and the characteristic of the fault. However, considering that one side of the fault is short-circuited and the other is open, what will happen is that the current value taken on one side of the fault will be taken as reference current. And when the device moves to the top of the fault, the current value will change due to change of impedance, and the current value will be 0 on the open circuit side of the fault. So I'll now discuss a little bit of the current progress and results. This technique proving section. The technique of our concept has been proven in 3-way verification. That is, that we have created mathematical models. The matrix is shown in my presentation calculates the currents produced in the device, induced in the cable sheath, and induced in the cable conductor. We've created electrical models on Simulink, MATLAB Simulink. We also created finite element analysis models on ANSYS Maxwell. And the results produced by these 3 models are very closely matching and therefore verifying the technique. We also went through a device design optimization stage, where we initially investigated a 3-phase operation device, as shown in the video. It consisted of a linear moving magnetic field inspired by the linear induction motor. However, the design operated very poorly. The magnetic fields interfered with each other, and the fields remained confined, as we can see in the video. This produced a very low power transfer efficiency. The coupling coefficient, which is a good means of measuring the power transfer efficiency, and ranges between 0 to 1. This device produced a coupling coefficient of less than 0.02. We then moved on to a better design. This was improved, and this was based on a single phase dipolar core design, which has a much improved field distribution and has a greater power transfer efficiency with a K of equaling greater than 0.1. The device also went through a coil optimization process, and below are a few examples of the different coil design tests. There's like 26 different tests, many tests we went through. Then the aim of the test was to achieve the highest coupling coefficient K. Again, we can see in the equation the had a significant factor for achieving a high mutual inductance between the device and the cable is the coupling coefficient K. Although self-inductances are also present, the self-inductances can be altered by changing the number of turns of and coil windings, which is it's kind of an easier process. It's K, which is the coupling coefficient, which is more significant. However, the study concluded that although many design techniques were tested and investigated, the most significant effect of increasing K was to reduce the large distance between the device and the cable, which is of about 80 centimeters, which is a burial depth. For example, design 3 showed the optimal results as it only contains a single coil of only 0.5 centimeters thick. So it has the least distance of the ferrite core and the cable, which is 80 centimeters dug underground. Design 2 generated a very high inductance, but had the lowest coupling coefficient due to increased distance between the core and cable. We also got preliminary results in our findings. These are the results for a 1 kilometer cable with a short circuit fault. However, the device electrical components are not optimized for optimal performance, and this is being to optimize the device performance. The electrical components, we're using particle swarm optimization technique. If time permits, I may discuss a little bit at the end. But for now, these are the preliminary results. As we see in the results, for monitoring the device, monitoring the current profile in the device, when the device is on the left-hand side of the fault, the device showed a current value of 33.26 amps operating. When the device moved to the top of the fault, the current profile of the device was 32.06 amps. And this is a fault distinction from left to top of 1.2 amps. When the device again moved from the top side to the right-hand side of the fault, it changed from 32.06 to 34.87 amps. This was a fault distinction from top to the right of 2.81 amps. And the similar was done for current profiles monitored at sheath and the conductor. This is available on my poster. If anybody would like to go see afterwards. So, we've also developed a guide to fault finding. See, we created a journal and submitted to IEEE. It's under review at the moment. It's titled as a comprehensive guide to fault finding in the underground low voltage distribution network. It distinguishes the applicable methods from IEEE fault finding standards. The flow chart presented illustrates the overall procedure. Prior to this, there was a lack of a structured guide for low voltage fault finding. Senior engineers trained new recruits from experience and time spent, and there was a lack of documentation available for training. So remaining work. As previously said, the remaining work is to tune the device parameters using particle swarm optimization. I have a few results right now. Unfortunately, they're not formatted for presentation, but there seems that we have solid results which hopefully may present next year. The next and also remaining part of the remaining work is to design and test the device's electromagnetic shield, and to examine the performance of the final model with a three-phase cable, with different fault types, with different fault scenarios, with the cable amongst other underground infrastructure, and to establish the performance limits of our device. Thank you for your time. Are there any questions?
Thank you very much, Khalif, for the interesting presentation. I think we have one question in the chat. I will transfer it to you. But if anyone wants to speak up as well, they can also do so. So I'm transferring the question. It's from Lara Santos. Says, thank you for the presentation. Is or could this electromagnetic solution be viable for subsea cable fault detection too? Or are fault detection techniques very different offshore?
Well, that's a very interesting question, and it's something which we are considering as well, because we want to make this universal for every single cable. However, my study of submarine cables are that they are armored, and this makes it quite difficult for electromagnetic waves to penetrate into and to pass the armor into the sheath or the conductor. However, if I can't say for certain, but if there is a pre-location done and there is a break in the armor, perhaps the technique may work. However, there are other techniques which will probably suffice, will be better, more suited. I have to admit that. This is mainly for the low voltage distribution network because, as I mentioned before, because of most pinpointing techniques specifically use thumping process, and which is detrimental to low voltage loads. So, and the cables are not armored neither. So this is more essential for the low voltage distribution network, as opposed to the medium voltage and the high voltage cables, where thumping can be utilized, and thumping is sufficient. However, it is important to note that high voltage thumping, etc., will also initiate dormant faults, and this is coming more into light. As mentioned previously, with custom interruptions and custom limits loss, yes, we want to have an effective fault-finding solution for custom limits loss, but it's counterproductive when you're fault-finding and then creating more potential custom interruptions by initiating dormant faults in the cable. I hope that answers.
Thank you very much. That's very comprehensive response. So thanks a lot, Khalif, for this.
Thank you.
Do we have any further questions from someone? If not, maybe a very quick one from me, because we have a minute or so as well. So does the method that you're proposing, do you have any feeling of whether it has any increased cost related to the device that you are suggesting effectively?
Increased cost, sorry?
Compared to, for example, thumping technique that you say it's the common approach, basically. Is this going to be much more expensive as technology, or you don't?
Well, TDRs, there are plenty, the amount of technologies adopted for the field team are quite a lot. There's quite a lot of technology. There's quite a lot of equipment which is required for fault finding, because there's quite a lot of types of faults and scenarios, and the different methods will be suited for different scenarios. We can't, and the cost will be a one-off cost. It's just buying the device, isn't it? It's just buying the device, and the device, it doesn't really require anything else other than perhaps, because we already have monitoring devices, coupling, just current transformers, which are applied for other techniques such as thumping as well. So that's already available for the field teams. It will only be the device, and at the moment, I can't say for certain how much the device will cost, but it's only a one-off device that you'll get, just like all the storage generators will be one-off, etc. And it's not like there's no running cost to the device, if that's the question.
Very good. Okay, thank you very much, Khalif. I think that covers me. I think in the interest of time, we probably can proceed to the next presentation. But if you have any further questions, I'm sure Khalif would be happy to take them offline with you as well. So feel free to get in touch. So the next speaker is Orestis Angelidis from the University of Glasgow, talking about district heating and cooling. So I will invite Orestis to the stage. There he is.
Perfect.
So whenever you're ready.
Yes, thank you, Panagiotis. And so today we will be talking a little bit on district heating. So we will switch a little bit to the thermal side of things and see what's happening on that side of the world. As I mentioned, we'll be looking into how can we decarbonize heat, and then start investigating the district heating and cooling concept, which is quite fascinating. And this is what I'm researching in more detail, see some of the key themes of research and outputs, and then kind of put it all together with a summary and a take-home kind of digestive set of outputs. So kind of what we will be talking about is the decarbonization of heat. And more specifically is how this can be done in a holistic way. So thinking about the whole system altogether, what's the impact to the electricity grid, and how, if we are to look at the whole energy trilemma of security of supply, low cost, environmental impact in a holistic way, what sort of opportunities we have there and what benefits we can have. Now, the project is with the University of Glasgow. There's a lot of stakeholders. So there's the public part, which is the ETP, as you're aware of. There's Rumble, which is the industrial partner, University of Glasgow and the University of Edinburgh. So let's start off with why. So why actually decarbonize heat and cool? Now, in 2019, the Scottish government actually issued a climate emergency And as you're all aware, this is a major challenge that we need to face in the upcoming years. Now, about a third of the UK's overall CO2 emissions actually come from heating, and more specifically for the domestic, industrial, commercial sections. Now, the major part of these emissions do come from cities. It is expected by 2050, 75% of the global energy use will be coming from cities. And this is due to the very big urbanization trend that we're seeing. And it's also interesting is to think that other than the heat consumption that is it's rising, it's like the heating that we need at homes, hot water, there's also rising cooling because of the anthropogenic effects of these cities and the heat island effect. So we expect it to triple, so be 3 times as big as it was in 2006. Now, the simple decarbonization solutions would be to simply just be on top of the electricity grid. So stick some sort of direct electric heating in our houses or direct electric cooling, or go into the alternative of just individual air source heat pump solutions, which are like air conditioning units, which I'm sure you're all aware of, especially if you're kind of from the south. So from Greece, where I'm from, you can, it's in the middle of the summer and it feels like it's raining at times if you're close to the pavement, simply from the water that is dripping down from these air conditioning units. Now, the problem with this is that the cost of electricity in the UK right now, it's 5 times the cost of gas. So we're going to be pushing a lot of people into fuel poverty and having a difficulty of actually reaching a level that is satisfying in their houses. So there's both the cost, the efficiency, and the strain on the electricity grid that is the problem if we go with these simple solutions. And if we're to add on this is how could we actually incorporate the city and interconnection of utilities in that idea of decarbonizing heat? How can we make use of the digitalization that is happening with more than 83 billion services and kind of sensors that we're expecting to have connected? How can we make use of this? How can we make sure that we're reusing energy, and rather than seeing things separately, how can we actually look at the whole thing together? How can we have a holistic approach? Now, an initial kind of answer to that would be to have a conventional district heating or district cooling network. And the concept here is that you have your heat or cool generated in a central location and then sent out to individual homes or offices or whatever you can imagine through a set of pipes that looks like an electricity grid, but instead of cables, you have pipework. Now, this is not something new. It's been around since the late 1800s. Most of the Nordic countries have it. So all of Copenhagen is built this way. And it's slowly coming to the UK for different reasons. But again, here it would be separate. So we would just have district heating or just have district cooling. So what if we were to take this a step further? And this is the idea that I want to kind of discuss more today. So the concept of district heating and cooling. So essentially we have one network of pipes for both, not 2 sets of pipes. And the concept here is that we can make use of the fact that somebody's heating is somebody else's cooling dump. So if somebody needs to cool down their data center or their tube station, we can use that heat, re-put it in the same network, and use it further down the line in dwellings. Now, we don't have centralized energy production. We have decentralized. So we have satellite substations that upscale either the heat of the cool of what we need, and we have the ability to have a bidirectionality in terms of both energy and mass flow within these pipes. Now, because we will be using heat pumps again, we can use that coupling with the electricity grid because they run on electricity. So we have a lot of opportunities of coupling the whole system together. So what would be the key pillars of this technology? It would be circular economy. So there will be that transaction of energy in terms of heat and cool within the same system, especially in an urban center. We can make use of a lot of scattered waste and heat opportunities within these cities. And we can address the rise of cooling needs that we're expecting without some sort of expensive and really hard to implement new way of approaching it. And maybe we can have a shift to the paradigm of how we see the energy sector. So we can have a shift from the monopolistic management of a centralized energy supply company, as we have at the moment, to a more open heat production by using prosumer. So we can have that everyone's both a producer and a consumer. Now, the overall system performance, by the way that I've been talking about it, it's evident that it's perfect and it's great and it's the new step. But that's really not the case. So if we are to look at the economic, environmental, and energy use part of things, the system still has a lot of limitations. in terms of both its flexibility to change and maybe expansion, its robustness, because it's a lot of complications added, so maybe we're actually taking steps backward instead of forward. The complexity, the strain on the electricity grid by having a lot of units could be actually worse than having a centralized unit that we can more easily kind of couple with flexible tariffs or other concepts of how we can kind of have that interaction. And then that business model it's something new, it's risky, so it might even be something that doesn't really make sense in the larger scheme of things. So by looking into all of those, I came up with 6 themes to kind of go through and capture all of these. It would be a first comparison to this with these kind of 6 key performance indicators. How would it compare to this traditional 4th generation district heating and district cooling? Then what would be the physics of operation? How can the thermal grid act as a flexibility element? What is the role of thermal storage to that excess heat maximization? And then how can we model all this? So we've captured all this, but how can we model it? And how can we have that new business model that kind of ties it all together? So I've been doing a review on this, and as you can see, most of the research is within the last 4 or 5 years. It's very fragmented. It's a very fancy graph to show that, but it has that wow factor. So that's why we're going with it. And on the right, you can see that there's a lot of different countries that are looking into it. They have different names for it. Even the way that the technology is called is not settled upon. So in order to kind of infuse this concept within my literature review, I actually contacted a lot of stakeholders from various backgrounds. I think right now we're about 25 or 30 from a range of countries to actually get their views on these 6 themes and try to see what their views are. Now, the opinions were split because there was emphasis on different components, because there's not really a quantified way of seeing this, and rather it's quite qualitative. And everybody expressed an interest in a thorough, extensive literature review on these to kind of go through the key parts. Now, we are running low on time, so we're going to quickly go through these, but this is just to give you a taste. And you can prepare your questions. This is like just a sense for that. So starting off with that comparison, it seems that the co-occurrence of the factor of the energy demand for cooling and heating and their seasonality has a key and critical role in terms of when the system is performing better or worse. If we're just to look at heating, for example, a centralized kind of conventional system would always perform better, as Goodmanson et al. Proved through their research. The spatial characteristics is another really big component, along with the thermal storage and the level of retrofitting that we need to have. So what temperature we require and the phasing levels. The physics of operation become quite complicated. So the bidirectionality of flows in terms of both mass and energy, and how we arrange the hydraulics of the whole system, how the substations come into play, and how can we avoid a lot of hunting or a lot of instabilities within our system. The demand side management is also something that we can use, since we have this decentralized substations. So it's something that we can do in order to reduce the peak. The thermal grid, in terms of how it comes to the flexibility element, we can have thermal batteries. So we can have the buildings themselves become like a thermal battery to what the electricity grid is doing. We can also help balance the grid and shave a lot of the peak and shift it to hours of lower demand. The electrical capacity that we need to build within our cities can also drop. So there's a lot of benefits from that. In terms of thermal storage, the physical characteristics are kind of better sometimes by having that decentralized and satellite effect, and the environmental impact that it could have can also drop. In terms of modeling, there's a lot of different ways of approaching it, but there is a gap in terms of a simulation that is not too high level or not too in-depth, and that offers both acceptable computational times, but captures the physics of the system. And finally, looking into that business model, we can have this heat and cool as a service, and how we can have with the prosumers concept moving from that monopolistic business unit to an open market. How can the digitalization of smart cities become a lot more democratic, and how can we use a lot of novel opportunities from donor economics or crowdfunding or participation of the public within decisions into how we build up and go from simple consumers to active members of how the energy sector is built. So where should we stand? And I'm closing with this. The situation is really not clear. It seems to be a case-by-case evaluation needed. So having a tool that would allow us to make this comparison and having a map of when it's better to go, so setting up the boundaries for it, seems to be critical for moving forward with this technology. And that could allow us to look into this new paradigm of energy systems and see when we can go with it. Now, these are exciting times to work on this, and for sure, I'm really happy to kind of start looking into both the social and the simulation aspects of it. So future search for me is to combine all this fragmented research, highlight these both industrial and academic gaps, and try to fill them through the modeling and be having a simulation tool that is open access, and we have some very valuable outputs that we can then map and show when we can use one and when the other. Thank you very much for your time, and open for questions. Run a little bit over time, but yes, if we want to continue this discussion, very happy to do so through either LinkedIn or email. Yes, it'd be great to have your thoughts. Thank you.
Thank you very much, Oresti. That was an interesting presentation. So opening up to questions now. Does anyone have something to ask to Orestis? There's currently nothing in the chat, so I'll take the chance to... Oh, so there's something just came in. So very insightful presentation, Orestis. Thank you. What is the best example of this working in practice?
Yes, so there are a couple of networks. So at the moment, we have about 40 or 50 pilot schemes throughout Europe and some in Canada. The best one that I'd say is, like, you can check Ectogrid. If you just Google Ectogrid, is Ion's project in Lund, in the Medicon Village, and it shows how you can have this interaction and this kind of circular economy coming into practice.
Very good, thanks a lot. And since I don't see anything else, maybe a quick one from me as well, just being mindful. Oh, no, another one came, so I will prioritize the other one. Missed the beginning of the presentation. Which of those outlined 6 areas you think is the most challenging and why?
That's a very interesting question. Frankly, most of them. But I would say the key one... Okay, so firstly, it is the physics. So it is the complexity of how you model this, because you have these bidirectionality of mass. The whole thing becomes very complicated to actually track and see how the pressure drops and how you can avoid hunting within your system, how you can avoid hydronic imbalances and instability within your system. Because one of the key problems that we see, even with proven technologies like, let's say, combined heat and power or similar approaches to thermal networks, is that you design them and then you put them in place and they don't work. So sadly, we have a lot of cases in the UK, for example, in London, that you have networks that should be, flying, but you end up just using gas boilers because the controls are not quite as good as you thought or too complicated, and you made a hole in the water. So I'd say that that's the biggest trick. And then obviously it's the social aspect, which is we have a new system. We need to approach it with a new view in terms of a business model. We can't have a new system with old paradigms of how it works, because it's inevitable to fail.
Very well. Thank you very much, Oresti, for the answers. I think in the interest of time, we should move to the next presentation. Again, perfect questions, you can take them offline. Feel free to do so. Next one is Arsad from Glasgow Caledonian University, talking about investment decisions in electric grid transmission systems. So I will invite you to the stage, Arsad. Perfect, you are ready. So whenever you are ready, go ahead.
Hello. I'm PhD at Glasgow Caledonian University. Today, I'd like to present my research topic. This is an analytical research project that aims to explore the impact of different parameters of the electric grid, probability of failure, consequence of failure, and overall network risk. In collaboration with ESPN, this research project aims to provide with insight into impact of asset management decision process defined by model, inform future investment strategies, which may be introduced as a requirement for the next round of price control Rio 3. So currently we are inspecting the impact of electric vehicles and space heating on distribution system. Electric vehicles share in transportation is increasing every year. In general, electric vehicles load is 7 kilowatt for the slow chargers, 50 kilowatt for the rapid chargers, and 250 kilowatt for the superchargers. More use of electric vehicles in future years can influence the maximum and average demand. This will account for higher electrical stress on the transformers, and therefore the electric vehicles has the potential to stress the distribution and transmission transformers. So in general, the definition of end of life of an insulation system is the point at which the insulation no longer performs reasonably. So in literature, we can see that there is a established relationship between the increased loading due to the probable electric vehicles penetration to the net distribution system. We see the more electric vehicles are charged through the network, to the distribution network, it ages faster. So in the winter, it becomes worse. So and we have developed, we have found that due to the increased average load, the end of life of the transformer is increased so fast, like 2.5 times if the transformer is loaded above 100% or near to the 100%. And for the maximum demand, it is around more than 120%. So it is simulated for the transformer is loaded at around 100% for 8 years. And after that, comparing with the general case, for example, if the transformer is loaded at 50%, it becomes it has 2.5 2 times the general aging. It has 2.5 times the aging of due to the electric heating and the electric vehicles load on that network. So from this graph, we can compare it with the probability of failure, because the maximum demand has a relationship with the transformer end of life, and end of life has a relationship with the probability of failure. So we can get a relationship between maximum demand and probability of failure, and this will give us a relationship between the increased demand and the monetized risk model for the network, because it is essential to estimate how much risk the electric vehicles and space heating is bringing to the network, and whether the network will need to be upgraded in near future. So this is the graph for the maximum demand relationship with the probability of failure and the average demand with the probability of failure. It is being developed at this moment. So in next 6 to 7 months, I hope it will be completed. So here we have, it is important to estimate the electric EV charging loads. By superimposing the estimated EV charging demand and space heating demand on currently available power demand, we can estimate the increased overall network demand. Then we can estimate the increased aging rate of the network assets, for example, the transformers, bus bars, transformers, transmission lines, and other assets. Moreover, we will be able to estimate whether the current infrastructure will be able to withstand the increased demand or it needs to be upgraded. So to calculate the overall EV demand for the network, at first we need to understand the EVs will not be starting charge at a time. So it will gradually build up the charging, and after some electric vehicles that started charging earlier, that will finish the charging and it will stop taking charge from the electricity from the network. So it will gradually reduce the demand. So we have simulated the scenarios for different times. For example, for the night time, when the EVs are charged at night, and midday and evening, we can see this data is provided from SPIN for Sprango Valley, and we have also data for Devilmore. And we can see for this transmission transformer, on an average, the load is around 9 megawatt, and it goes up to 12 megawatts. So at night time, the load can be increased up to like more than 50%. So it can go up to 15 megawatt for this case. And if for the now, if we also need to consider the EVs, the electricity EV users' arrival to the workspace, because the EVs users will may arrive to the workspace and start charging at the workspace. So we'll be considering that as well. And EVs take some time to charge, and when they are plugged to the charger, so we will be considering the duration of each charging of each EVs in the network. So next we have the data provided by ESPN. This is the data provided by ESPN, and from there we have developed this one. And next, if we consider that the EVs are charged slowly over the 6 hours, so we have a lower demand, peak demand for the network. So comparing with the 3 hours and 6 hours, we see the overall increase of peak demand is much less for the 6 hours. So the strategy that we can follow is the flatten the curve. So we can use smart charging, so that the network is not highly affected due to the high power demand of the EVs. And next, we need to discuss about the space heating. In general, that we have a data from the 2012 report, and here we see that the houses that doesn't have any electric heating consumes 600 watts at most, but the houses that has additional electric heating has a peak demand of around 900 watts. And the houses that are primarily electric heating, uses primarily electric heating, has the scenario is completely different. So we have the peak is around 2 kilowatt. So combining the electric heating and EVs loads to the network, the distribution system and the transmission system can be highly loaded for the electricity demand, and it may affect the transmission transformers and distribution transformers in near future. And this is what we are at this moment analyzing, and understanding if the network is need to be upgraded in maybe 5 to 10 years from now. Thank you for your time. I would like to have some questions from the audience if they have. Thank you.
Thank you, Arshad. Thanks a lot. Very, very interesting stuff, relevant to what I'm doing as well. So I quite like your presentation. I have some questions, but again, I will prioritize anything that comes in through the chat, or anyone maybe from the presenters wishing to speak up and ask a question. So any questions for Arshad from the audience? So I will take the chance to sneak in one from myself, potentially if people are typing in. So because you work both with the heating and the EVs, so in terms of estimating how the network usage will change, do you find it easier to do for heating or for EVs? Like the estimation part only, not the problem as an entire challenge, but the estimation part.
The heating part is not done yet, but the electric vehicles part is going to be is run, and we are doing that at this moment. So I'm finding it a little bit difficult to do the EV part, because it is there's so many uncertainties regarding the starting time of the EV starting charging, and also the ending time of the charging. So, and there are different type of EVs available in the market. Their ratings are different. For example, Nissan Leaf has 24 kilowatt hour battery. Some other electric vehicles has different battery capacity. So it's a little bit difficult to calculate the EVs.
Very good point. Yeah, absolutely agree with you. I think it's challenging. It's not an easy problem. Right. So maybe any other question that someone else would like to ask? Okay, so maybe it's just a very quick one then from me in that case. So because you mentioned the start end of charging and so on, so did you do this in a kind of a case study manner, or did you use any probabilistic method to
probabilistic method I have used here.
Perfect. Okay.
Because I did not get sufficient data from survey reports, so I used the probabilistic distribution function for estimating it.
Very good. Yeah, that's very interesting. Okay, thanks a lot, Arshad. So in that case, I think we can move to the next presentation. And if any questions come up, obviously, you can follow up with Arshad. So the next speaker is going to be Samuel from the University of Edinburgh, talking about hybrid distribution transformers, right? So I will invite Samuel to the, okay, there we go. So Samuel, whenever you're ready, go ahead and start.
So, hello, I'm Samuel Hayward, and this is the presentation for my PhD project being done with the University of Edinburgh, titled Coordinating Smart Hybrid Distribution Transformers to Support Local Clean Energy Systems. So to start off with, I'll provide some background to the project. So in order to help combat climate change, the UK government have set targets for reducing carbon emissions, and this will likely lead to an increase in the implementation of renewable distributed generators and electric vehicles within power systems. And distributed generators, for anyone who's unfamiliar with them, can refer to this figure here, where on the left we see a conventional network where power stations connect to transmission networks, whereas on the right we see examples of distributed generators which connect to distribution networks and are physically closer to energy consumers. However, distributed generators and electric vehicles can cause power quality issues within networks, such as voltage violations and harmonic distortions, which make networks less reliable. As such, there's an increase in technologies that can help mitigate these power quality issues to allow for greater implementation of distributed generators and electric vehicles. One of these technologies happen to be hybrid transformers, which are the focus of my project. And this figure here just helps to visualize the concept in which hybrid transformers are used within distribution networks in order to allow for distributed generators and electric vehicles. So what is a hybrid transformer? A hybrid transformer is a combination of a conventional power transformer and power electronics. The inclusion of power electronics provide the transformer with additional capabilities such as adjustable voltage regulation, harmonic mitigation, and power factor improvement. Shown in this figure here is that there are several different configurations of hybrid transformers, with different configurations potentially having different capabilities. In regards to project goals, there are 4 main goals. The first goal is to develop steady-state models of hybrid transformers for simulation purposes. The second goal is to develop control and coordination strategies for when there's several hybrid transformers within the same distribution network. The third goal is to create an energy system design framework which incorporates hybrid transformer models and their characteristics such as sizing, placement, and topology. And the fourth and final goal is to assess what value hybrid transformers could add to the UK power system, and this would be accomplished through large-scale simulation of hybrid transformers implemented into distribution networks. So this project is partly funded and supported by a company called Ionate, who are developing their own hybrid transformer, and they are providing us with information about the functionalities and capabilities of the transformer, which are then being used to help characterize the steady-state model for this project. Ionate's hybrid transformer uses magnetic control, which just means that the power electronics influences the operation of the transformer through the use of auxiliary transformer windings. Ionate's hybrid transformer has the following capabilities: adjustable voltage regulation by plus or minus 10% the RMS voltage, power factor improvement by plus or minus 0.85, harmonic distortion mitigation, and also independent phase voltage control. So in regards to the steady state model, it will simulate the adjustable voltage regulation and power factor improvement capabilities of Ionate's hybrid transformer. And it will be similar to a combination of a reactive power compensator and a transformer with either a on-load tap changer or variable transformer ratios. And this is because reactive power compensators can provide power factor improvement by minimizing the magnitude of reactive power within certain portions of a network. And on-load tap changers are able to provide adjustable voltage regulation to transformers by changing the effective turns ratio within transformer windings. And just here's a diagram of the steady state model in which you can see the combination holds true. We have a reactive power compensator, in which case is connected to the primary side of the transformer, providing power factor improvement to incoming power signals, and a transformer with variable transformer ratios for each voltage phase. So the control of the hybrid transformer will be simulated through the use of optimal power flow. Optimal power flow being a method of determining the optimal operation or behavior of a network in relation to specified objectives and constraints. For the hybrid transformer model, the objective function will be to minimize deviations from the nominal power factor and voltage level. And this will be accomplished by making adjustments to the transformer ratios and the reactive power injections. The open platform for energy networks, also known as OPEN, is the simulation environment that we are using to test and model the steady state model and the hybrid transformer control schemes. It is a collection of Python packages and custom files that allow users to simulate electrical networks, and is based on the ZBus modeling method, in which networks and network components are modeled as admittance matrices. And Open is used as opposed to other simulation environments, as it offers greater flexibility and customization, which is ideal when trying to model and simulate a new novel network component such as hybrid transformers. Upcoming project work for the near future includes implementing the optimal power flow controller for the steady state model. Then we will go on to determine if the model and controller appropriately simulate the behavior and operation of the hybrid transformer. For this step, we will consult INATE for advice and feedback, just to ensure that the simulations are appropriate. Then we'll go on to test the optimal power flow controller for the control and coordination of several hybrid transformers within the same distribution network. And again, we will consult INATE for feedback and advice. And finally, in regards to the near future, we will determine if the model and controller are able to allow for greater implementation of distributed generators and electric vehicles within certain test networks. Looking further ahead into the future, if there is still time in the project after completing the 4 main objectives, which I discussed earlier, there may be additional work in developing a dynamic model of the hybrid transformer, which would be used to simulate the frequency regulation capability of INATE's hybrid transformer. Unlike the steady state model, the dynamic model would work within smaller time intervals. The steady state model works with time intervals of about 30 minutes to 1 hour, whereas the dynamic model would work within time intervals of about 1 minute. So just to summarize the project overall, this project is focusing on modeling and simulating hybrid transformers in order to demonstrate whether or not hybrid transformers can allow for greater implementation of renewable distributed generators and electric vehicles within distribution networks. And if the results of these tests and models show that hybrid transformers do allow for greater implementation, this demonstrates that hybrid transformers can potentially be used to help the UK government reach its carbon emission reduction targets, and as such help the UK government in combating climate change. And the results of this would then help to accelerate the adoption of hybrid transformers into the UK power system. That is it in regards to my presentation. If any of you have any questions, I'll now take them.
Thanks a lot, Samuel. Interesting presentation. We already have one question in the chat from 2 of them, sorry. From Khalif, the first one. Hi, Samuel. What simulation tools are you planning to use to model the hybrid transformers?
The simulation tools right now for the steady state model is just going to be Open and other available Python packages that might be useful for future work. The dynamic models, for example, will probably use different simulation tools, perhaps MATLAB and Simulink. However, at the current moment in time, since that is not a obligation of the project, we haven't really decided yet. But just for now, it's Open and other available Python packages.
Okay, that's good. Thanks a lot, Sam. And second question from Lubika. Hi, Sam. Is the idea to replace the standard transformers with the hybrid transformers? That's a first step. And there's a second step. Is there any limit for voltage? In other words, are they designed for the high voltage distribution mainly?
To answer the first question, in the case of Ionate's hybrid transformer, this would be a replacement because Ionate's hybrid transformer requires different physical dimensions to conventional power transformers found in distribution networks. There's a different shape to the iron core. However, hybrid transformers in general, it is possible to retrofit the power electronics into pre-existing power transformers depending on circumstances. So in the case of this project, while Ionate is providing information, the overall goal of the project is more just to show the benefits of the capability. So it would depend on the circumstances of whether or not the conventional transformer is replaced with Ionates, or perhaps another hybrid transformer altogether is retrofitted in. Could you repeat the second question again? I forgot.
Yeah, absolutely. Since we are at it, a quick follow-on question on that from my side. So do you have any feeling, let's say, of the actual benefit of using this proposed structure where you mentioned it's doing some control of the magnetic field maybe and not directly the electrical? So is there any particular advantage of going through that route rather than any other route? Or to be honest, the simplest thing, maybe have a FACT device next to a conventional transformer, as you mentioned. This would be an equivalence, basically.
I can't really name it off the top of my tongue because while we are using Ionate's hybrid transformer for the replicating the functionality, the actual innards of the transformer I'm not too familiar with. I understand the connections as such, but I believe the benefits may be in regards to the ability in regards to adjustable voltage control, whereas it allows for much more granular and precise control of adjusting the voltage as opposed to other more conventional means of having the fax device connected through conventional direct connections.
That's a good point. Yeah, I mean, I understand that there is a lot to the technology basically behind that, and that you are just using it to model your network. Yeah, that's a fair point. So the second question is, which is slightly different, if there are any limits for voltage. In other words, is this designed for high voltage distribution network mainly?
In regards to voltage limitations, we are not really considering that at the moment because Ionate's device, as I mentioned, is still in development. So Ionate intend to have their device to be, they intend to have a customer base in which different parts of distribution networks, both higher voltage and lower voltage, will be considered as potential customers. So for the sake of the project, we're just going with the assumption that we can just add the hybrid transformer into any distribution network. Ionate did give certain voltage levels, however, I cannot recall them at the moment for the intended initial release of the device. But both high and voltage level distribution networks are being considered as their potential customers.
Very good. I think that answers the question. Thanks a lot, Samuel. I don't see anything else in the chat, so I think we should move to the next presentation, again, in the interest of time. I think we are doing well, so that's good. We are on track. So the next presenter is Agatha from University of Edinburgh, talking about virtual synchronous machines. So Agatha, whenever you are ready, you can share your slides and feel free to go ahead.
Okay. Hi, everybody. My project is titled Virtual Synchronous Machine Control and Design Requirements in Voltage Sourced Converters. So first, I'm kind of define all those sort of buzzwords in the title. Going to look at a specific type of converter, the MMC, then explain a bit about what frequency support is, and then the role of inertia and how virtual synchronous machines can be used. And then I'm going to just show some quick results from a study I did. Okay, so a voltage source converter is an umbrella term for a type of power electronic converter, which is in the title of my project, but I really only focus on modular multi-level converters. That's because these are used extensively in the transmission system, and there's many more that are being built of in the sort of near future and are planned. Basically what they do is convert between AC and DC power. Normally this would be in the sort of point-to-point configuration, and that's because it's much more efficient to transfer large amounts of power in DC than it is in AC, and it also allows you to connect two different networks which aren't synchronized. So for the UK, that's particularly useful. It means that any connection to mainland Europe or Ireland will probably be one of these MMC HVDC connections. We do have one and another planned, I think, that's sort of embedded in the network because of the efficiency gains for the long distance transmission. So in the pictures here, you can see actually this picture here is an offshore converter station, and that's because, again, when a wind farm is really far out, at some point it becomes better to convert the power to DC for the efficiency savings in transferring that power back to shore. And it would come into an onshore converter station that looks like this, just to give you an idea of the size of these stations. And inside both of these will be a valve hall that looks something like that, which is where the electronics actually are that's doing the conversion. Okay, so an MMC is made up of hundreds of submodules. Each submodule has a little capacitor inside it and some switching electronics. And for every time step, the correct number of capacitors are switched either in or out so that you get this sort of stepped waveform, which is an almost perfect sinusoidal wave. It's much more close to what you would get from a synchronous machine than any other type of converter, and that saves you a lot of money on filtering, which is another reason why this MMC is what's sort of the entire industry at the moment. Okay, so the other part of this project was about virtual synchronous machines, and they are used to help maintain frequency stability. So to try and define frequency stability a bit, the transmission grid is an AC system, and the frequency that system is at can be thought of as a sort of balance between supply and demand. In the UK, when supply and demand are totally balanced, you get 50 hertz. Then if there's some kind of fault and you lose some generation, in this little example, we've lost a wind turbine, you'll see that the grid frequency begins to fall. That is a pretty bad thing, because as the grid frequency falls, other devices protection could start tripping more generation off or more supply off, and the whole thing loses stability, and you can get like massive cascading failures. Almost any big power cut you can remember will be because of something that cascaded through the network. So you really want to make sure that the frequency stays stable. The role of inertia in that is that inertia, based on this equation, controls the rate of change of frequency. So in this sort of diagram, this point here at the end of the grey box is the point where National Grid, or whoever is the system operator, has responded to the drop in frequency by adding some of their generation reserve onto the system, or and worst case scenario, they remove some load. The higher your inertia and the lower your rate of change of frequency, the longer they have to do that, and also the less severe any event is, and the faster you get back up to your nominal grid frequency. However, inertia does come from, traditionally, it came from our coal plants and our gas plants. So as you can imagine, that the amount of inertia on the grid has been reducing for a long time now, and we expect it to continue to reduce. So that's where virtual synchronous machines come into it, because we'll need something to replace that. Otherwise, we'll just keep losing stability much more frequently than we are now. And yeah, so the basic idea of a virtual synchronous machine is that it would mimic a synchronous machine. And the behavior that it really needs to follow for that is, if there's a change in grid frequency, then there has to be a change in the power that the converter produces. That's the sort of basic building blocks of a virtual synchronous machine. So this is the active power output of a virtual synchronous machine and a traditionally controlled grid following machine responding to this very perfect grid frequency event shown at the top. So you can see when the grid frequency drops, the virtual synchronous machine active power output shoots up, whereas a traditionally controlled converter wouldn't. So in this situation, you might have a little bit of, you might have slowed down the rate of change of frequency on the whole system, allowing the reduction in the chance that any fault is going to cascade across the network. So yeah, then if that all works, what's the problem? Why don't we just shove that everywhere? So basically, there's quite a lot of different barriers to adoption of this type of control. A big one is the energy required. If you're going to increase the power output of a converter, that has to come from somewhere. So if we look at this diagram is of a proposed scheme between England and France. And if we imagine a situation where England is importing their the power across the link to France when there's a lightning strike or something, and the frequency falls on the English side. That means, as we've just seen in the previous slide, the active power has to increase, which, okay, I mean, we've got all of France here, we've got some cables. So do we just increase the AC to DC conversion here? So if we assume that the European network is perfectly happy to do that with no warning and still maintain their stability, which is a big if, but even if we assume that, then we're still going to have a time delay here, because the amount of time it will take for this converter to see this grid frequency change and then request extra power from France is going to be significant in the lifetime of a fault. So as I said before, an MMC does contain some capacitors. So in theory, it has a little bit of stored energy. Each of these cables has a capacitance. So again, there should be a tiny bit of stored energy there as well. So what I've been looking at is what are the physical limits to a situation like this if we start to drain the capacitors on the English side here until the French side can ramp up the export across the DC link. So I produced lots of little images like this. Each little square on this image represents one simulation that had a frequency change given on the x-axis here, and before the frequency event happened, what was the power export on the side that had the event. So we can see that we can see here that the current limit was very unlikely to be hit if the frequency didn't change, which is, as you'd expect, that's just steady state, and that the larger the frequency change, the more likely it was for the current limit to be hit, and for the current through the converter to exceed what would be considered the manufacturer's limit on what's safe. As well as the current limit, I looked at the voltage limit, which is reached if the converter can't physically produce the voltage that's required by the simulation. For this situation, it's normally because the capacitors actually don't have enough energy and then we've drained them too much, so the converter isn't able to reach the required voltage. And then finally, we looked at the energy limit, which is very connected to the voltage limit, but it's to do with the theoretical limit of energy that is needed for correct operation to be carried out. That includes things like cooling. So that's why nothing on this side has been reached, because in this situation, there's actually extra energy flowing into the converter. But then I added them all together to create a sort of operating area. And you can see by looking at that, it mostly matches to the current. So the current limit is the main one, that we found. So the conclusions to that work was there is a little bit of capability, there is a little bit of frequency support leeway there, but it definitely requires that the converter is operating below 1 per unit before any fault occurs, which means that it would definitely have to be financially supported. The converter owner doesn't want to operate below 1 per unit unless the regulator would have to pay for that in some way. But then the next steps are definitely to look at how the limits that I found could be expanded using just some control changes, and also to have a look at, you know, adding some batteries or other storage into the system to reduce the need for that fast ramp across the DC link as well. Okay, so thank you very much. Has anybody got any questions?
Thank you very much, Agatha, for the very insightful presentation. I don't see currently any question in the chat, so I will take the chance to ask something myself and maybe give it a minute or two for others to type in their questions if they are doing so. So from my side, I was wondering, I've seen you use the term virtual synchronous machine. So I was wondering, is this the type of control that you have taken into account, or have you looked at other so-called grid-forming controllers as part of a particular scheme?
Yeah, so the answer to that question depends on how you define virtual synchronous machine, which isn't consistent. I have taken into account lots of different controllers. Some people define a virtual synchronous machine as a controller that models the physical parameters of a synchronous machine, which isn't. So the results I showed you with the sort of the power going up for the frequency change, that was one of those types of controllers that I'd modeled, but the results at the end wasn't one of those. That was a controller that was based on droop control, which is simpler, but probably I think maybe a bit more effective.
Okay, yeah, very good. Thanks a lot. I have follow-on question to that, but I'll jump to the chat because Ludwika has a question for you. So first of all, great presentation, Agatha, very clear and giving a great insight. Which one is more vulnerable to be balanced in case of frequency drop, voltage or current, and why?
Which one is more vulnerable? I'm not sure I understand. When the frequency drops, it's a power imbalance, so it's voltage times current, right? But generally speaking, because the grid will be the transmission system will be at a certain voltage anyway all the time. So if you want to increase the power for the power injection, it's going to be a current increase, really. Normally, when we talk about changes in voltage in virtual synchronous machines or grid forming, it's to do with them balancing reactive power. So I hope that answers it.
Yeah, I think that covers it. Yes. Yeah. And we have another question coming up in the chat from Natasha. Oh, it's not a question, it's a comment. Very good at clear presentation. So
it's just compliments, you know?
Yeah, that's good to hear. Yeah. So I think we might have maybe a minute or so to sneak in another question. So probably that I can just a quick follow-up on what you were saying about VSM, VS grid forming or droop control. So which would you imagine being the main, let's say, difference if you swapped from VSM to another, to the droop control, to make it more specific? In terms of, because you presented thermal voltage limits and what was the last one? Energy, right?
Energy.
So, yeah.
Okay, so if in the kind of fault I looked at, which I think isn't necessarily the most accurate, I suppose when you start taking transients and stuff into account, if you use a droop controller and you're comparing to the rate of change of frequency, you should get a spike at the start of the frequency event and then it will fall back down again, as opposed to if you get a sort of square response to a drop in frequency. So in terms of thermal limits for say the power electronics, there's more likely to be a bit of leeway in the droop because the peak current is probably going to be held for much less time than in the virtual synchronous machine.
Very good. Very interesting. Thanks a lot. I think we can now, thanks again, Agatha, for the presentation. We can probably move to the next and last presentation of the session as well, which is Timur from the University of Strathclyde, talking about an autonomous unmanned eco-robotic surface vessel. Sounds very, very interesting. So can we have Timur on the scene, on the main stage? Sorry. Yeah, that's perfect. Thanks a lot. So Timur, whenever you're ready, go ahead.
Yeah, thank you. Okay, Matthews, I will go on with the full screen.
I think we can't see your screen at the moment. You need to share it. Have you tried sharing your screen? There is a button at the bottom of your screen.
Actually, sorry.
I don't. I still, for me, I can't see your screen. I don't know if it's the same.
If this is fine, actually, I'm just having a big problem with my Windows program. So.
Okay, so is this maybe something that we can do? I don't know. Maybe William, can we try something else, or Matthias?
Yeah, I'll just try and share Timer's presentation, and if you want me to switch across the slide, Timer, just let me know. So if you just bear with me 2 seconds, I'll just get that up.
That's perfect. Thanks a lot.
Sure.
Very
you can share my slides. Thank you for that.
Okay, just give me a second.
Okay, perfect. Okay. So if I can ask you, Timur, if you can keep it a little bit more concise so that we keep to the time, because this is the last presentation as well. So that'll be very useful.
Thank you.
Thanks.
Thank you. Actually, I think we're ready to go for that, and my sincere apologies for all this inconvenience. Actually, I'm presenting the ocean drone eco-robotic surface vessel. Sometimes it's called electric vessel, and it's actually a project carried out in collaborations with the Dynamic Power System Laboratory and the company working in the electric vehicles and in the transitions of energy to a clean energy. So I will move to the next slide. Let me just share the highlights of the slide. So we actually worked on for the ocean drone and have developed the electric vessel, the computer data, power converter base, its modeling and control, and the most important part of the whole project have been the energy management system. And another interesting thing has been the performance analysis using the real-time data, and real-time data has been taken from 3 different scenarios of the sea, which actually corresponds to the weather conditions and the effects that actually put in the losses of the power converters and overall performance. So from here, the architecture actually, which is the electric vessel structure was actually defined in the horizontal and vertical surface. So we had to opt for the dual Mppt based power converters. And further from that, the main objectives and the option was to increase the redundancy in the system. So obviously some control and power converter topologies were selected, which actually again which actually can enhance the redundancy in the system as well as reduce the losses in the system. So based on this, we just included the fuel cells, which were baked by the power converter, which was actually giving the hydrogen reserves and the onboard vessel. Further, since such type of vessels and components have the very sensitive components and the apparatus on the board, so we just included a 3-stage output voltage supply, and on the back end the whole system was actually the independent power converters, and it was actually industrial controller based control. Yeah, interesting thing has been the bidirectional converters were also part of this, and the battery energy storage system was connected to there to stabilize the DC bus and keep the system out of transients. Going to the next slide, so we have the dual Mppt topology, which was connected in the manner on the left side. We can see, so it was actually controlled using the PI controller and the perturbator observer. Basic algorithm was adopted for the complete the extraction of power. On the back end, each distributed Mppt converter is actually controlled using controller and was extracting its maximum power for stabilizing the DC link in any of the requirements and demand by the loads. So the important part of the project was the BSS control and the DC voltage, DC bus control. So on the left side, just a part of the overall development, the flow chart is actually have been working that if we have a VDC is greater than V reference, obviously this turns to the that if we have a surplus energy that is more than our reference voltage, so we are checking yes or no conditions, and if we have the voltage more than is this, then we are going for the battery energy system SOC are checking, and if that is more than 70%, so obviously we are balancing the overall power system DC bus of 48 volt, otherwise we are charging the battery. Similarly on the left side, if the SOC is less than 25%, so the overall bus of 48 volts is then maintained for fluctuation and all by the another emergency BSS that has been included in the architecture. So apart from this, just to include the redundancy of the system of the Offshore drone, just because it has to go in the on the missions for 24 hours or so. So obviously, based on these complete power converters and the resources of the PV fuel cells and batteries, we are actually working on the to increase the redundancy. So based on that, we just included the fuel cells and the power converters. So the fuel cells were actually self-controlled in a different manner, just to control its power, and including a ramp function for that, just because fuel cells are not in a dead way that they actually respond to a very fast transient. So in a ramp way, their control was centralized and was responding for any of the demand that is to be discussed in the next slide. So the energy management system has been the main core of this overall project, which was developed along with the architecture of the overall scheme as well as the control algorithms, power converters. So it actually does that real-time monitoring of power demand and supply according to the observer or who is operating the vessel is shown. Another thing is that it actually monitor and control the hydrogen for demand and supply, and ensuring the redundancy in the system by showing the alarms or something like that. And yeah, the most important thing is keeping the electrolyzer turning on for balancing the hydrogen demand supply. So this is actually what we did in the energy management system. If we just go to the next slide, so a very simple and less computationally energy management system based architecture was itself defined just to reduce the cost, the computational burden of the system, and to increase the redundancy. So based on that, if we just see that the PNet of the PNet is actually the power from the PV plus hydro. So if there is more than the overall load of the all vessel, the overall load is the 24, 12 volt, I mean the 3-stage voltage, and the battery itself. So if there is greater than the overall load, so we just set the reference of the fuel cells to 0, so the fuel cells are not contributing to the overall power supply, and then we are charging our batteries. Similarly, if there is not less than also, we are actually contributing the power from the fuel cells by setting the reference of the power from the fuel cells, which is the difference of the power between the load and the overall net power that is generated between the hydro and the solar panels. In case of that, if we have any of the surplus, so we are going to the left side and charging our batteries. The more we have power, so we are turning out the electrolyzer that actually stores the energy in the hydrogen tanks for the future supply. And based on this, we just increase our redundancy in the system and mission endurance. So different tests was carried out based on the real-time data, and considering the latitudes of the origins. We just took the irradiance and the temperature graphs with that, and the overall data, and 12 simulation based scenarios were conducted for 24 hours. And the main conditions were to check the redundancy of the system was that to check the BSS with full hydrogen tank and the charged BSS with no hydrogen tank. This was actually into the mission profile, and what we monitor was the power demand and supply, SCC of the batteries, and hydrogen management in these all. So this is the one of the 12 results we actually showing that the North Sea was taken for the high season, and full storage was there, and the full battery and the vessel was into the was left in the sea. So we see that the total energy produced by the renewable energy was 17 kilowatt hour, and the 25.48 was consumed by the load. The battery SOC was 100%, and at the end of the 24-hour journey, it was a candid 100%, meaning the battery delivered power in the 24-hour scenario, but again, it was able to charge from the PVs or from the fuel cells and all this, and the mission endurance was 10.1 days. Similarly, the same test case was carried out for the North Sea high season, and the previous was for the low season. So in the same way, but we over here we just check that if suppose we don't have the hydrogen and we are not operating the fuel cells, so the mission endurance was 2.67 days while operating the PVs, and total of 25.4 kilowatt hour of load. Here is just a summary of the charged BSS with 7.5 kg of reserve hydrogen for 24 hours of mission for the North Sea, Arabian Sea, and Sicilian Sea for the high and low season in all three. So if we just see it for the Sicilian channel, we just had the highest mission endurance of 17.1 days. That means that if we have a 7.5 kg on board, the reserves and charged BSS with PVs, so that is 17.1. And in case we don't operate with the FC, so we have 3.66 days, and that is a very traditional one on board, and I mean in the market that already exists. So such sort of system exists, and coordinating with fuel cells, it actually increased with 17 days of mission endurance. So that's what we are more increasing it by including control system. In conclusion, efficient power system architecture integrating PV, fuel cells, and BSS was developed. Independent control loop was developed, and real-time manufacture data was used for all these investigations and analyses. And the highest mission endurance that was achieved was 22 days. But keeping in mind the losses associated with the sea and the overall partial shading, and also we just included 30% losses and 85% conversion efficiency, and in that case we just got 17% of the mission endurance. And overall these were validated using the real-time data of the 3 different regions. Thank you very much, and if anyone has any questions, please let me know.
Perfect. Thank you very much, Taimur, for keeping on time as well. So any questions from anyone, feel free to type them in. I will quickly sneak in one from my side because we are kind of running out of time as well. So have you built the hardware for this as well? I know you concentrated on the EMS system, but did you also build the hardware?
No, Haru is actually part of the exam. This was actually a 3 months project, so we just worked and did, and we are further increasing we are have intentions to make it with the RTDS, some very real-time results of the all things, but until now we are in process of developing the hardware.
Very good. Yeah, that's very interesting. Thanks a lot.
Thank you.
Okay, so I don't see any other questions coming up in the chat. So probably I think we should wrap this up. I think we are very much on time. So thank you everyone for keeping to the time. Thank you for the interesting discussions and presentations. This would be the time for a big round of applause, but we are doing this virtually, so not much we can do here. But I think this was a very interesting session, very nice discussions, very nice work presented. So again, thank you all very much for being here today with us. And hopefully we'll get to meet soon as well at some point in the future. So I think we can call it the end of the session, and we can all go to the lunch. I wouldn't want to keep you longer here. Oh, I would also like to thank very much William and Matthias for the technical support to run this very, very, very smoothly. I think we managed to do this as smooth as in the best possible way, basically. So that was great. Thanks a lot, everyone.